Imagine standing on an ocean of grass. No trees, no rivers, no walls, no stores. The temperature drops to minus 30 degrees Fahrenheit overnight, and the wind cuts through everything like a blade. You have no metal, no ceramic, no factory, no map. Now imagine not just surviving here, but building a civilization that lasted for centuries. Most people, when they think about the Native Americans of the Great Plains, picture warriors on horseback, feathers, fire, a romantic image painted by Hollywood and forgotten by history textbooks. But what those images never show you, what nobody talks about, is the engineering. The cold, precise, brilliant engineering hidden inside a single animal, the bison. One creature, roughly 2,000 pounds of muscle, bone, organ, and hide. And the Lakota people found a way to turn every single part of it into a technology so precise, so efficient, that modern scientists who study it are still quietly impressed. In this video, we're going to open that system piece by piece. You'll discover how a gallbladder became a self-cooling water flask that outperforms most modern canteens in direct heat. How hoof material produced a structural adhesive so chemically sophisticated it's still used today in the finest string instruments in the world. And how a pair of dried lungs became a biological barometer that gave more reliable storm warnings than anything European settlers had for the next 200 years. Every chapter in this video is a door, and behind each one is an engineering secret that took centuries and countless lives to perfect. Stay with me until the end, because the last secret we reveal isn't just impressive, it will change the way you think about what the word primitive actually means. You are 3 days into a hunting patrol across the summer prairie. The temperature is above 100 degrees Fahrenheit. The nearest river is 30 miles behind you. The clay jug you started with shattered on the second day, and your horse is beginning to slow. What do you carry water in? The Lakota answer was already inside the animal they hunted. The bison's gallbladder possessed a combination of physical properties that made it nearly perfect as a portable liquid container. Its muscular walls were thick enough to hold significant internal pressure without rupturing. Its tissue was naturally impermeable to moisture, and unlike clay or carved wood, it weighed almost nothing when empty. After careful removal, the organ was rinsed thoroughly and scrubbed on the interior surface using fine river sand and smooth stones. This wasn't just cleaning, it was chemical neutralization, removing every trace of bile that would otherwise contaminate anything stored inside. The cleaned bladder was stuffed tightly with dry grass to hold its shape and hung in shade, never direct sunlight, to dry slowly over several days. Rapid drying would crack the walls. Slow drying transformed the soft tissue into translucent, flexible parchment. Lightweight, durable, ready. When filled, the flask held over a liter of water. When empty, it collapsed flat and fit inside a belt pouch. But here is the detail that separates this from any simple organic container. The walls of the dried gallbladder allowed microscopic evaporation of moisture through the tissue itself, creating a continuous, passive cooling effect on the liquid inside. This is evaporative cooling, the same physical principle that powers modern swamp coolers and that ancient Egyptians used in clay vessels as far back as 2500 BCE. The Lakota arrived at the same solution independently, using what was already available inside the animal they depended on. A traveler returning after a full day under the open sun could still drink cool water from this flask. No factory, no mining, no trade route, just a deep understanding of what was already there. Now consider a different problem. You are building a composite hunting bow, a weapon that must bend to near its breaking point with every shot, survive temperature swings from minus 20 to plus 90 degrees Fahrenheit across a single season, and hold together under the full mechanical stress of a warrior's draw without a single joint failing. What do you bind it with? Modern engineers use epoxy resins and synthetic polymers. The Lakota use something that predates all of it, and that professional luthiers who build and repair violins and cellos still choose today over synthetic alternatives for certain critical joints. Collagen adhesive extracted from bison hooves. Hooves are composed primarily of keratin and connective tissue, rich in structural collagen. When broken down through prolonged, controlled heating in water, the collagen partially denatures and dissolves into a thick, viscous solution. As it cools, The protein chains reform into a network that bonds with extraordinary strength to porous surfaces like wood and bone. The critical variable is temperature. Collagen begins to irreversibly break down above approximately 70 degrees Celsius. The Lakota craftsmen had no thermometers. They read the surface of the water, the size of bubbles, the behavior of the foam, the sound of the simmer, and maintained the correct temperature through observation alone, often over several days of continuous tending. The resulting material was stored by winding it warm around thin sticks, hardening into compact portable rods that kept their properties for years. On a composite bow, this glue bonded layers of wood, horn, and sinew into a single unified structure, joints that didn't crack in cold weather and didn't soften in heat. Arrowheads set in this compound could survive direct impact against bone without separation. A hunting weapon built without a single piece of metal, bound entirely by a material extracted from an animal's legs, performed well enough to sustain an entire civilization's food supply across the most demanding terrain on the continent. And the formula hasn't been improved upon in certain applications, not in 500 years. There is something historians rarely discuss when they talk about nomadic societies. How do you maintain social order when you have no coins, no written contracts, no permanent buildings, and no courts? The Lakota had an answer, and it fit in the palm of your hand. In every large bison hunt, the distribution of meat followed a communal system. Families received shares. The elderly were provided for. No one went without. This was not charity, it was engineering. A community where anyone starves is a community that fractures, and a fractured community on the Great Plains does not survive the next winter. But within that system, there existed one exception, one cut that never entered the communal pot, one part that moved in a completely different direction, upward. The bison tongue. Anatomically, it is a dense muscle marbled with fat in a way that almost no other part of the animal was, given the lean physiology of a wild bison. In a diet built largely around tough, lean meat and dried provisions, this texture and caloric richness made it something genuinely rare, not just as food, as experience. It was served at councils, at treaty negotiations, at ceremonies marking significant transitions. A chief who offered this cut to a visiting leader was making a statement that required no translation. I give you the best of what I have. Refusing it was not simply impolite. It was, in the social language of the plains, a declaration. Here is the detail that most accounts leave out entirely. By the mid-19th century, commercial hunters arriving on the Great Plains would kill a bison, cut out the tongue, salt it, and ship it east to restaurants in St. Louis and New York, leaving the remaining 1,800 pounds of the animal to rot on the ground. To a Lakota hunter, this would not have been waste. It would have been incomprehensible. On January 12, 1888, a blizzard swept across the northern Great Plains with almost no warning. Temperatures plunged 40 degrees Fahrenheit in a matter of hours. Wind speeds reached 60 miles per hour. Visibility dropped to zero. Hundreds of European settlers, farmers, school children walking home, workers caught in open fields, died within miles of shelter they could not find in the whiteout. The storm became known as the school children's blizzard. It killed an estimated 235 people across the Dakotas, Nebraska, and Minnesota. The Lakota had been living in this same climate zone for generations. Records of similar mass casualties among plains tribes are significantly harder to find. Part of that is the absence of written documentation, but part of it is that they had a warning system. It didn't look like a warning system. It looked like a dried organ hanging near the ceiling of a teepee. The bison's lungs, when removed intact and carefully dried over weeks in the warm air near a teepee's central fire, became what we would now recognize as a hygroscopic sensor, a device that physically responds to changes in atmospheric moisture. The organ's internal structure, composed of millions of microscopic air sacs surrounded by fine connective tissue, becomes extraordinarily sensitive to changes in humidity and pressure once fully dried. In the hours and days before a major weather system arrives, atmospheric pressure drops and relative humidity rises. Organic porous materials absorb this moisture and expand, not dramatically, not visibly to an untrained eye, but readable to someone who had spent years observing this specific object. A slight softening of the tissue, a subtle increase in volume, a change in how the material responded to gentle pressure from a fingertip. Experienced observers could reportedly distinguish not just the approach of bad weather, but its intensity. When the signal was clear, the response was immediate. Women reinforced the teepee coverings. Men moved horses to sheltered ground and secured every external joint on the portable structures. We should not overstate what we can verify historically, but hygroscopic expansion in organic porous materials is a documented physical phenomenon. The principle is real, and the Lakota's centuries-long survival record in one of the most climatically volatile regions on Earth suggests their observational systems were working. They didn't know the term atmospheric pressure, but they built their entire survival calendar around understanding exactly what it does. Stand on the Great Plains in February and look in every direction. No trees. The tall grass prairie that covered roughly 170 million acres of central North America before European settlement was a landscape almost entirely without significant timber. The Lakota found their fuel on the ground. Bison herds in the pre-contact era numbered somewhere between 30 and 60 million animals. The precise figure remains debated. And everywhere they moved, they left behind dried dung in quantities that were essentially inexhaustible. The digestive system of a grazing ruminant processes plant material so thoroughly that what remains is a dense, compressed mass of cellulose fiber, a natural briquette. When dried completely, it burns slowly, consistently, and with sufficient heat for both cooking and space heating. The critical advantage is the smoke. Dry bison chips burn with almost no visible output. The Lewis and Clark expedition journals from 1804 to 1806 document their adoption of this fuel after wood became unavailable along the Missouri River, noting specifically the clean burn and consistent heat. For the Lakota, the smokeless quality had a strategic dimension. A column of smoke above the prairie is visible for miles. A camp that produced no visible smoke was a camp that enemy scouts could not locate by sight. The fuel you burned was also a security decision. Chips were stacked near each teepee in pyramidal formations, not decorative but functional, maximizing airflow to accelerate moisture loss while allowing rain to shed from the outer surface without saturating the interior. What looks like the ground's waste is in fact the prairie's most reliable energy storage system. How do you boil water inside an organic container, something made of flesh and membrane, without the container burning? The instinctive answer is, you cannot. And yet the Lakota did exactly this. Not as a survival emergency, but as a refined daily cooking method. The answer lies in a single physical principle. Water boiling at 100 degrees Celsius cannot exceed that temperature while it remains liquid, regardless of how much heat is applied. The tissue of a bison's stomach sustains serious thermal damage only at temperatures significantly above that threshold. The water acts as a thermal buffer, protecting the organic walls not through their own heat resistance, but through the physics of the liquid they contain. A freshly cleaned bison stomach was stretched between 4 wooden stakes driven into the ground, creating a suspended basin holding 30 to 40 liters, enough to feed an extended family. Beside this vessel, a separate fire heated smooth, dense river stones. Not just any stones. Porous rocks absorb water into their structure and explode when heated rapidly. The Lakota selected granite and quartzite from riverbeds specifically, accumulated geological knowledge built through generations of observation, and the painful education of stones that shattered unexpectedly. Red-hot stones were lifted with wooden tongs, cleared of ash, and lowered into the liquid. The water erupted into immediate, vigorous boiling. As each stone cooled, it was removed and returned to the fire, while a fresh one took its place, maintaining a sustained boil for as long as cooking required. Into this went meat, wild onions, prairie turnips, dried berries, and bone sections that released marrow and collagen into the broth. The vessel remained intact. The physics held. Modern bushcraft practitioners who attempt stone boiling today consistently report the same finding. It works well, and it works fast. The Lakota had simply known this for centuries before anyone thought to write it down. Every civilization needs a way to hold things together. Metal cultures used rivets and wire. The Lakota turned to the connective tissue bundles running along the bison's spine and through its major muscle groups, sinew. The biological cables that transmitted the force of a 2,000-pound animal's movement from muscle to bone with every stride. Dried mammalian tendon can achieve tensile strength in the range of 80 to 150 megapascals, comparable to certain grades of aluminum alloy, substantially stronger than most natural plant fibers available on the Great Plains. Long white strips separated from the spine were cleaned of fat, laid flat under direct sun to dry, then placed on flat stones and struck with smooth river rocks in controlled rhythmic impacts. This progressively broke down the rigid structure without severing the longitudinal fibers, until individual threads could be drawn out by hand. When moistened with saliva, these threads became pliable enough to pass through holes punched in rawhide by a bone awl. As they dried within the seam, they contracted, pulling the joined pieces together with increasing force, creating a seam that tightened itself. A mechanical property no plant fiber thread could replicate. Clothing and footwear constructed this way were nearly windproof and highly resistant to moisture penetration, not through any waterproofing treatment, but because the seam itself closed under tension. On a composite bow, sinew applied in multiple layers to the back of the weapon provided the tensile reinforcement that allowed it to be drawn to forces the wood alone could not sustain. The bowstring itself, twisted sinew cord, did not stretch under load, did not soften in humidity, and did not snap under the mechanical shock of a full power release. The bow that a warrior carried into a hunt represented not just his own skill, but the accumulated labor of the people around him. Every shot was a collective achievement. Remove metal from human civilization completely, and the entire architecture of daily life fails simultaneously. No blades, no nails, no needles, no scrapers, no structural fasteners. A single bison skeleton weighs between 90 and 130 kilograms. To someone who knows what they are looking at, that is not a pile of bones. It is a hardware store. The broad, flat shoulder blades attached to wooden handles became hoes, capable of breaking compacted prairie soil. The natural curve of the bone positioned the working edge at an angle that reduced the force required, a geometry that modern ergonomic tool design would recognize immediately. The long curved ribs translated directly into sled runners, lashed to wooden frames for transporting loads across deep snow. The long tubular leg bones split lengthwise into blanks for needles, awls, scrapers, and cutting tools, resharpenable on any rough stone, in the field, within minutes. Bone marrow carried separate nutritional value. A single large femur from an adult bison contains sufficient marrow to provide several hundred calories in highly bioavailable form, rich in fat and fat-soluble vitamins. Pemmican made with bone marrow fat reaches a caloric density approaching 3,500 calories per pound, comparable to modern military ration concentrates. After marrow extraction, the emptied bones were simmered to extract residual fat used to condition leather, protect wooden handles from moisture, and lubricate equipment in cold weather conditions. Nothing was discarded. The sequence of uses extracted value from the bone at every stage. The horns operated on a different material logic. Bison horn keratin is impact resistant, naturally waterproof, and does not crack in cold the way wood does. When submerged in boiling water, the keratin structure softens enough to be manipulated, widened, flattened, curved, formed around a wooden mold, and retains the new shape permanently as it cools. This thermoplastic behavior is a property we now associate with synthetic polymers. The Lakota were working with a natural version centuries before the concept of a polymer existed in any scientific vocabulary. Sealed horn sections served as containers for live coals during travel. A smoldering coal packed with dry ash to restrict oxygen could be kept alive for an extended period, arriving at a new campsite with fire already in hand. In wet conditions, or extreme cold where hands lose dexterity, the ability to carry fire, rather than make it, was not a convenience. It was the difference between arriving and not arriving. We have reached the last secret, and it is the most remarkable, not because of what it produced, but because of how it worked, and how long it took the rest of the world to understand why. Raw bison hide allowed to dry without treatment becomes rawhide, stiff as wood, brittle and cold, unwearable as clothing. The transformation into soft, supple, durable leather required a tanning process that was, in its underlying chemistry, genuinely sophisticated. The tanning agent was the bison's own brain. The brain of a large mammal contains significant concentrations of lecithin and other phospholipids, molecules with one end that attracts water and one end that repels it. In chemistry, these are called surfactants. In industrial leather production, synthetic surfactants perform exactly the function that brain tissue performs naturally, penetrating the collagen fiber matrix of the hide and coating each individual fiber, preventing the fibers from bonding to each other as the hide dries. This is what tanning accomplishes at its most fundamental level. Not hardening the hide, preventing it from hardening. The fresh hide was stretched on a wooden frame and worked with bone scrapers until every trace of flesh and membrane was removed. Physically demanding work occupying the better part of a full day. The brain was extracted, combined with water, and slowly heated into a smooth emulsion, then applied to the dried hide in multiple passes, worked in by hand to ensure full penetration. The treated hide was bundled and set aside for fermentation, hours to days, while the phospholipids continued migrating through the collagen matrix. Then came the most demanding stage. The hide was stretched, pulled, twisted, and rubbed against rope or a wooden stake for hours in its partially dried state. The brain-derived phospholipids provided the lubrication. The mechanical working provided the separation. Together, they produced a hide that dried soft. The final stage was cold smoking over slowly smoldering rotten wood, chosen for dense smoke at low temperature, without significant heat or flame. The smoke deposited phenols and aldehydes that cross-linked with the collagen, locking the softness permanently. Brain-tanned leather not smoked will revert toward stiffness if it gets wet. Smoked brain-tanned leather could be soaked completely, wrung out, dried, and remain soft. This property, wet buckling resistance, was not consistently achieved in European commercial leather until modern chemical tanning processes in the 19th century. The Lakota achieved it with smoke and time. Industrial tanneries of the 18th century used oak bark, urine, and mineral salts in processes taking months, and still did not match what a skilled Lakota woman could produce in a week, using materials derived entirely from the animal she was processing. We use the word primitive carelessly. We apply it to people who lived without steel mills and electricity grids, without the industrial infrastructure that modern civilization took 500 years and an entire planet's resources to build. But consider what we have walked through together. A water container using passive evaporative cooling, the same principle in modern cooling systems. A structural adhesive still chosen by professional instrument makers over synthetic alternatives. A biological barometer requiring no calibration, no batteries, no replacement parts. A fuel that burned cleaner than wood, left no visible trace, and was essentially limitless. A cooking method applying thermodynamic principles without a single piece of manufactured equipment. Thread with a self-tightening mechanical property no synthetic thread of the era could replicate. Tools from a skeleton covering every functional category metal serves, and a leather tanning process achieving wet buckling resistance a full century before industrial chemistry caught up. 9 systems, 1 animal, 0 waste. Not because the Lakota lacked options, but because they understood something we, surrounded by disposable everything, have largely forgotten. Efficiency is not about doing more with more. It is about understanding what you already have, deeply enough that nothing is left over. The Lakota did not conquer the Great Plains. They read it. They learned its language, the language of grass and wind and bone and pressure and cold, with a patience and precision that took generations to develop and could be lost in a single generation of disruption. Much of it was lost, not through failure, through force. What remains is enough to make one uncomfortable observation. We did not replace this system with something better in every category. We replaced it with something faster, something that scaled, something that could be owned and sold. And in doing so, we discarded solutions that were, in several measurable respects, more elegant than what we substituted. That is not romanticism. That is materials science. That is thermodynamics. That is chemistry. The people who lived on the Great Plains before contact were not waiting to be civilized. They had already built one, quietly, completely, and in perfect equilibrium with the only environment that mattered, the one they actually lived in. If something in this video made you stop and reconsider something you thought you already understood, that reaction is worth something. Share this with one person who would find it genuinely interesting, not for the algorithm, because ideas this precise deserve more than one viewer. And if there is a civilization, a survival system, or a lost technology you want us to examine with the same depth, tell us in the comments. We read them, and the best suggestions become the next video.